Hey everybody, back. Right now we're going to talk about applications of vectors to physics because really understanding lots of different objects, movements related to physical objects or how things move or forces acting on objects, vectors are the way to think about them. So uh, look at this example. Here we have a weight hanging from two different uh, points. So we've got some cords here that are connecting these points to a weight, and um, how much, once we've set this up this way, the question is, well, how much force is is there on this rope, and how much force is there on this rope? And the reason we might want to know that sort of thing is because if there's too much force on a rope, then the rope is going to break. So in this setup, the question would be, well, how much force is there on each of the ropes? And so when you're approaching this type of problem, the key concept is that at this central point here, there's the force of the weight pulling down, there's the force of the rope pulling uh, in this direction, and there's the weight of the force pulling in this direction. And what we have to recognize is that at that point, the forces all have to cancel out. Because if the forces aren't canceling out, then that point's going to be moving. And because the point is not moving, then the force being exerted by this rope, the force being exerted by this rope, and the force being exerted by this rope, they all have to equal out. And so we're going to use that property to write down some equations, and that's going to tell us how much force there is on this rope and how much force there is on this rope. Okay, so uh, we're going to set up, so the way we can do that is we can set up a coordinate system. You can set up your coordinate system in many different ways. At this situation, it's easiest if we set up our origin of the coordinate system right at that point where all the ropes meet. And so what we'll need is we'll need to know how much force is there pulling in the positive x direction, the positive x direction, the negative x direction, the positive y direction, the negative y direction. All of those forces have to add together to give the zero vector so that the point isn't moving. All right, so let's draw this picture. We have a force pointing down, and we have two forces pointing in those directions. And we need the sum of those three vectors to add up to the zero vector. So how much force is there pulling down? Well, we see this 100-pound weight. So um, the thing with physics is you always have to worry about the units. As mathematicians, we're often just dealing with numbers and we care about the numbers. But in physics, we're going to need to care about the weight, about all the units. And so as a quick aside, here we see this 100 pounds. Pounds is a weight. And the only thing, so whenever you're dealing with pounds, you don't have to do any conversions. That's already a force information. Um, you may have heard about the metric version of this, and then you see kilograms, right? Kilograms, though, is a mass. And so if you want to convert a mass to a weight, then you'll have to take whatever your mass is in kilograms, and you'll have to multiply by 9.8 meters per second squared. Right? This is gravity. So that becomes a weight. So in particular, what we have is we have metric, we have US, UK, we have mass, and we have weight. So for metric, we have kilograms, and when you do kilograms times meters squared, you get newtons. And in the US, we deal with weight, which is in pounds. And I'm just wondering, have you heard about what the mass unit is for the US system? Most people haven't. It's actually called a slug. But we don't use that when we're okay. When we're doing calculations, we normally deal with the pounds. But this is just a note that if you were doing this problem and it had kilograms, you'd have to put everything into newtons, which you get by multiplying by this 9.8 meters per second squared. All right. End of the aside. Let's get back to solving this equation. What we need is we need the force, or this weight, this mass force. The force in each of the directions. The force is a vector. It's being pulled in this direction, or pulled in that direction, or pulled in that direction. This is being pulled down at 100 pounds. So we can write that as a vector, 0, negative 100, because we're pulling down at a certain rate. And this negative 100 is because this is in the negative y direction. All right, so now we need to figure out what the vectors are for the force in the other two directions. All right, so what we're going to do is we're going to let F1 be the force. The force be with you. Okay, so F1 is equal to, is a number. So it's the magnitude of the force. But what we need to do is we need to write that as a vector. And so what we're going to do is we're going to take this triangle, and we're going to use it to say how much of F1 is in the negative x direction and how much of it is in the positive y direction. All right, so we've got this vector, and we're going to break it down into a vertical component and a horizontal component. And so to do that, we're going to need to use some trigonometry. So we see this 50 degrees here, and we know that the adjacent part of this is going to be F1 times, so adjacent is cosine of theta, and the vertical part is F1 times sine of 50. So F1 is the hypotenuse, sine of 50 is opposite over hypotenuse, and so when we multiply that by the hypotenuse, we get the opposite. So F1 sine of 50. So this first force is equal to F1 times sine of 50. So sorry. What's the x component? The x component is this part. So it's negative cosine of 50, comma positive sine of 50. Right? And where am I getting the positive and the negative from? I'm getting them from looking at our coordinate system, which says that this is the positive x direction, and this is the positive y direction. And so we're going in the negative x direction, but we're going in the positive y direction, and that's why we have these values. Okay, so F1, the vector, is equal to F1, the number, the force, times negative cosine 50 times a comma positive sine of 50. Right, this is the magnitude times the direction. Similarly, so here we have F1, so minus sine of 50. Let me make sure I got that right. Nope, so that was negative cosine of 50. This is why I go back and check. So negative cosine of 50, comma sine of 50. And now let's do this for F2. For F2, we have a vector, we have our triangle, and we see that the 32 degrees is here. The hypotenuse has value F2. So again, this is the adjacent, so that gives us the cosine. So this is F2 cosine of 32, and this is F2 sine of 32. But in this case, they're both positive values because it's in the positive x direction and in the positive y direction. So we have positive cosine of 32, comma, positive sine of 32. So we have our two vectors. We actually have our three vectors, right? We have our vector pulling down. We have our vector pulling in this northeast direction, and we have this vector pulling in the northwest direction. And so now if we write an equation that says W plus F1 plus F2 equals 0, equals the 0 vector, then we can solve that and figure out what F1 and F2 are. All right? So we have our two equations. This is our vector from the x coordinates, and this is our equation from the y coordinates. All right, so I'm going to go back a couple of slides and I'll show you where these come from. But what we're going to be in the lookout for, let's be on the lookout for this equation. What we want to see is we want to see the y coordinates add up to 0. All right, so let's look at the y coordinates here. The y coordinates are negative 100. The y coordinate here is f1 times sine of 50. And the y coordinate here is f2 times sine of 32. And because these three vectors add up to 0, then these three coordinates have to add up to 0. So that's saying sine of 50 times f1 plus sine of 32 times f2 minus 100 is equal to 0. And similarly, the x coordinate also happens there. We have two equations, two unknowns, so we can solve, and we get this equation. So I suggest, there's a couple ways to do that. You can use your calculator, you can use Mathematica, you can substitute, solve for f1, plug it into the other equation, etc. But this is telling us that pulling down is 100 pounds, pulling in this direction is 85 pounds, and pulling this direction is 65 pounds. All right, and let me just introduce two additional ways in which we can use vectors to talk about physics concepts, and we will practice these ones in class. So we can talk about work. So I think it's important to realize that there's the English word work, where you talk about, oh, I did some work today. But that's slightly different from the physics concept of work that says I'm applying a force which causes a displacement. So what I like to think about is okay, here's a cart moving up a hill, and maybe you're pushing. So you are pushing, and your pushing moves the cart up a hill a certain distance. So you're pushing in this direction, that's a force. And that ended up moving the cart in a certain direction, a certain displacement. So in order to calculate the work, you take this vector, this force, how much force was used to push the cart in a certain direction, and then you have this displacement vector d that moved, how the object was moved in a certain direction. That's this displacement. And so the work is equal to the force dotted with the displacement, 2 vectors. And realize that's going to give us a number, right? The dot product of 2 vectors is a number. All right, there's another example of a physical concept that uses vectors, and in this case it uses the cross product of 2 vectors. So this is useful when you're thinking about applying a force to some screws, right? So if you're using a wrench, here's my lovely drawing of a wrench. Here's a wrench, and you've got this screw that you're turning using your wrench. Well, you're applying, so in order to get this screw to move, you're pushing, you're applying a force to the wrench to turn the screw. So there's a vector here that has to do with your radius. So where you're applying the force. So are you pushing down on your wrench here? Or are you pushing down on your wrench here? Where are you pushing down? And when you do that, you've got a vector, a radius vector, from the pivot to the place where you push down. So this is, oops, sorry, this arrow, this is our radius vector. And then you're applying a force. Now, you can apply the force in a couple of different ways. Maybe you push down this way, maybe you push down this way. This is getting a little messy, but let's redraw this with a new color. So let's say you're pushing down at this spot in a certain direction. So this is our force being applied. When you do this, when you push with a force at a certain distance from the pivot point, then that creates a turning motion here. Right? This is going to turn the screw. It's going to either push it in or push it out. So going into the page, going out of the page, and to calculate it, you do torque is equal to R cross F. And because this is R is a vector, it's a vector from the pivot to where you're pushing. F is a vector, that's the force being applied to your wrench or to this to the lever. Then this torque is a cross product of those two things. It's also a vector. So in this case, it's going to be a vector either in or out of this, and you can use your right-hand rule to figure that out. Right? If we were going, let's look at what the right-hand rule would say here. We've got R, and F is a vector that looks like this. And so if I'm using my right hand, let's see how this looks. So kind of hard to do this. Here's what I'm going to do. I'm going to look over this. I'm going to stand over it. I'm going to put my hand in the direction of R, my right hand in the direction of R, and see which way I have to travel for the F to go to the F vector. And when I do that, when I put my right hand on the R vector and swing it to the F vector, I see that my thumb is pointing upward. And so this is telling us that the screw is getting a pull in the outward direction. All right, so that's it for today. We'll do some practice of that in class in class next time. See you soon.